Hi, and welcome to our fifth and final video on convective turbulence. In this video, we're going to look at flight planning. In other words, things that you can look for in weather charts and weather products to look for the clues that tell you about convective turbulence. And then afterwards, we're going to look at a case, a particular day when there was strong convective turbulence. So first, there are two different things that cause convective turbulence, either surface heating or cold air moving over a warmer surface. We're going to look at surface heating first. And of course, surface heating is usually, the turbulence caused by surface heating is usually found during the summertime when the sky is clear and the sun is high in the sky. So looking for clear skies, of course, what kind of weather products? Well, you can look at METARs or weather depiction charts. Surface analysis will tell you if there's clear skies. Also, you need light winds for this kind of convective turbulence, and you can look at weather products like METARs or the surface chart. But also, another thing is high pressure. And a region of high pressure you can usually find on the surface analysis chart. If it's cold air that's causing the convective turbulence, then you're going to look for the presence of a cold front on the surface chart. And behind the cold front, you're looking for cold air, of course, and you're also going to look for high pressure and light winds. So you can also use satellite to help pick out areas of cold air advection. What you're looking for is open cellular convection. And then the top of convective turbulence, in other words, the top of the mixed layer or the convective layer, usually can be found a few ways. One way is by looking at the pilot reports. If pilots reporting the tops of cumulus clouds, you can use that to fly above and get into the clear air, get a smooth ride. Also, area forecasts or the graphical area forecast you can use to figure out the tops of clouds. Otherwise, you can go to a sounding. We talked about how soundings will give you the tops of clouds sometimes. Another clue in the sounding is you can look for the capping inversion. Remember we said that there is a temperature inversion where thermals rise up to and stop, and sometimes that is present on a sounding.
Here's a case study from June of 2020. This is the surface chart. It shows that over the state of Illinois, there's not much going on. Looks like there's high pressure not too far away in New York. So this is on the backside of a high pressure system, still under the influence of that high pressure. There's no real weather systems in Illinois at this time. And the METARs show that for the most part, the winds are light or maybe even just 5 knots or so. And this is about noontime for the local area, about 18 Zulu or thereabouts. And you can see that there's also reports of few or scattered clouds, no real broken or overcast layers there. Here is the forecast for turbulence. This is the graphical AirMet for AirMet Tango, and it shows no forecast of turbulence over Illinois. Of course, remember that the AirMets only forecast moderate turbulence. Severe turbulence would be forecast by SIGMET. Light turbulence is not forecasted, so there's really no moderate turbulence or greater over Illinois. This is a forecast of clouds from the graphical forecast for aviation, and it shows that over Illinois, cloud bases are expected to be approximately 7,000 feet AGL over central Illinois, and the cloud cover is not that much. They're forecasting either few or scattered across that region. We're going to look at the sounding for Lincoln, Illinois, which is right smack in the middle of the state. And the identifier for the radiosonde station is ILX. Here is the morning sounding, and you can see that there is an inversion very close to the ground, and then also another inversion a little bit higher up in the atmosphere at about someplace between 800 and 700 millibars. I also put on here the dry adiabatic lapse rate. And you can move that actually just about anywhere as long as it's parallel to those red lines that represents the dry adiabatic lapse rate. So this is how a parcel of air as it rises through the atmosphere would cool if you forced it up, or if it gained enough energy that it would rise by itself. A little bit later at 0Z or 7 p.m. in Lincoln, Illinois, shows that near the surface the temperature warmed up dramatically, and it looks like the lowest layers of the atmosphere are very similar to the dry adiabatic lapse rate. They're parallel to the dry adiabatic lapse rate. And what this means is that at 7 o'clock that afternoon or that evening, when they sent up the radiosonde went up through the convective layer, the layer closest to the surface of the Earth. And as thermals rise and compensating motion sinks, pretty soon that lowest layer of the atmosphere becomes dry adiabatic from the rising and sinking air. So if you sent up a radiosonde, the thermistor on the radiosonde would measure the dry adiabatic lapse rate. And that's what you see here. Notice that the inversion from the morning is still there. The lower layer inversion disappeared, but the upper level inversion is still there. And that's what's preventing thermals from rising any higher in the atmosphere. The inversion base is about 780 millibars, which is very close to about 7,000 feet. Also notice that the temperature profile starts to get close to the dew point profile. So that at about 780 millibars, where we saw that inversion, the temperature and the dew point are less than 5 degrees Celsius. And if you recall from our discussion before about soundings, we assume that when the temperature and dew point are within 5 degrees Celsius, that there's probably clouds in that area. So this is where cloud bases are. They're right at that base of the inversion. And you know that thermals continue to rise above that inversion, the base of the inversion, because those thermals have momentum. And they eventually run out of energy, so that you'll have just a few cumulus buildups, and they're not very tall. We're going to look at the METARs for Lincoln, Illinois. The airport identifier is KAAA. Here are the METARs, and the latest METARs are on top and the earliest ones are on the bottom. This starts at about 12 Zulu and runs until about 1 Zulu in the afternoon or evening. And starting out in the morning, the winds are very light, visibility is great, and the sky is clear, allowing ample solar radiation to impinge the ground. But then about 11 o'clock in the morning, you notice that clouds start to develop. You got a scatter layer of 5,000. And then the next hour, it says it's clear, but that's probably because the ATSC machine, the ceilometer, missed the clouds. In other words, the ceilometer, the measuring device, shot in between the clouds. But you can see that throughout the afternoon, there is scattered to broken layer at 6,500. And those are cumulus clouds that are formed as a result of the thermals rising in the atmosphere. So you can see that also as the day progresses and the night starts to fall across the land, the sky starts going clear. In other words, these cumulus clouds start to dissipate after peak heating. They kind of start to fall apart, and overnight it will go clear again. Here are some pilot reports from across the region, and you can see where KAAA is. But these are just across the region. And pilots, I highlighted in red where they're reporting turbulence. Typically, pilots don't really report convective turbulence. They just bear it because it is annoying, and it's really hard for pilots to figure out when and where convective turbulence is going to be. For the most part, if you're flying in an afternoon during the summer, you can pretty much expect that you're going to get convective turbulence down low. And that's what they're showing here at CMI. They're looking at light turbulence at 5,500. At BMI, they're reporting cloud bases and cloud tops. You can see the cloud bases are at 6,500 and the tops are only at 7,800. So these clouds are only about 1,000 to 1,500 feet thick. So they're just really a kind of a thin layer of cumulus clouds. There's another pilot report at C09, which is very close to Chicago, reporting moderate turbulence at 3,000 feet. And also reporting clouds from 3,600 to 4,100. And then finally, near DuPage, just west of the DuPage airport, that would be DKB, you can see that they are also reporting light chop, a Cessna 172, and that is at 3,300. So this is how we identify convective turbulence, looking at soundings, looking at cumulus clouds, pilot reports, and then just good intuition. So I hope that helps you in your flight planning.